the normal strain is related to displacement, which is divided by the epsilons equal to the gradients of displacement divided by the distance x. And this actually the strain, if we can relate this to the, so this is the x system, and then this is our q or u. So if I have an element which is spanning from here to there, so this is my nodes number 1 and nodes number 2 of my element, then from the final element, then we found that the displacements of at nodes number 2 will be somewhere there, and at node number 1 is somewhere there, and at nodes number 2 will be somewhere there. So if we assume the linear distribution between the 2 points and we connect these 2 points, then we will have a straight line. So this is actually to show that the displacement at each nodal point. So from this, if we take the gradient of du over dx or dq over dx, so this is our dx, and this is our du or dq, then if we take the gradients or the slope of this, actually will give us the strain. And this equation du over dx also can be written in or as a functions of natural coordinate system by taking the chain rule of differentiation, where epsilons equal to du over dz multiplied by dz over dx. So next, let we solve this part by part. So we know that earlier that u x equal to n1 q1 plus n2 q2, and then we know also that z, the natural coordinate system, is given by 2 over x2 minus x1 multiplied by x minus x1 minus 1. So for the term of dz over dx, we actually differentiate the natural coordinate system dz by dx, which is, in order to solve this, I recommend you to expand this equation first, then differentiate it part by part. So if I can take example here, so the z here is also can be written as 2 over le multiplied by x minus 2 over le multiplied by x1 minus 1. So if we differentiate this dz by dx, so dx, then we will get 2 over le. So this will be 0 and this will be 0 as well. So this is what we get, and this is equal to the one that we have here. So to determine the expression for du over dz, then we solve or we differentiate the field displacement by the natural coordinate systems and z. So we know that u equal to n1 q1 plus n2 q2, which is also equivalent to this expression. And if we expand this, then we will get 1 over 2 q1 minus 1 over 2 q1 multiplied by z plus 1 over 2 q2 plus 1 over 2 q2 and z. So this is our u. So if we differentiate this by z, then we will get 0 minus half q1 plus 0 plus half q2. So if we simplify this equation, then it will give us this expression, which is du over dz equivalent to half of negative q1 plus q2. Thus, from that expressions of z equal to du over dx, which is can be written as du over dz multiplied by dz over dx, which is this equivalent to 2 over le. Then we have the term for du over dz, which is given by half of negative q1 plus q2. So this can be further simplified, and this will give 1 over le multiplied by negative q1 plus q2. Or we can further simplify this as 1 over le. So if we take 1 and 1 at the front here, so we have negative 1 and positive 1, and then we take the q1 and q2 and then put it in the column vector. Then we will have the expressions here where the terms 1 over le, negative 1 and 1 here will be called as the strain displacement matrix B, and then multiply by q. So this is how we derive the normal strains equation in the form of epsilon equal to B multiplied by Q, or the strain displacement matrix multiplied by the displacement Q. So in this slide, we will look at the stress-strain relation. So the normal stress is related to the normal strain by Hooke's law, which is given that the normal strain equal to the normal stress multiplied by the modulus of elasticity of the material that we use in our problems. So for solving the stress, we require the material informations. So we know that the strains is given by, as we derived just now, is given by B multiplied by Q. Then we, in order to relate the strain to the stress, then we include the material information, which is the modulus of elasticity, in our equations to obtain the normal stress equations. Alright, next let's we look at the element stiffness metric. So this in this slide, we actually to look at what is informations that contain in the K matrix, and also how we can derive this K matrix. So in order to derive the K matrix, or we call it as the element stiffness metric as well. So we will use the potential energy approach to derive this, but the derivations of element stiffness metric can also be obtained from other approach, which is we are not discussed here. So for the total potential energy of a body subject to loads is given by pi equal to u plus omega, where u actually refers to the internal strain energy, and omega, which is refers to the potential energy of external forces. So if we expand this equation for both internal and potential energy, then we will get these equations, which is, as we can see, we have four terms on the right hand side of this potential energy equation, where the first term here contains the informations of the stress, the strain, area, and the distance dx, or the length of our element. Then in the second equation we have Fb, which is the force due to the body force. Then we have in the third terms we have P here, which is referred to the traction force, and then we have PR, which is referred to the point load. So as we can see here in this equation, we have three terms that relates to the loading that acting on our elements. And since the bar has been discretized into finite elements, so we will solve this each of these terms discretely. So that means we are going to solve this according to small elements. Then in order to obtain the element stiffness metric from the potential energy equation, we will only need to concentrate on the internal strain energy, where so from this internal strain energy, which is given by half integrations of sigma t epsilon a dx, and we know that the normal stress, which is given by EBQ, then all of these we have to transpose it. So according to the transpose or matrix transpose, so the transpose of these actually equivalent to the E, then we multiply by Q transpose multiplied by B transpose. So this is the rule for the transpose, and multiplied by this normal strain, which is B multiplied by Q. So if we substitute these expressions for the stress transpose multiplied by the strain into the internal strain energy equations, then we will obtain these equations, which can further simplified, so that we have the internal strain energy, which is given by these equations. But this equation, as we can see here, is still returns in the Cartesian coordinate systems. So from this stage, we actually requires to rewrite this equation, so that this equation can also be read or written in the natural coordinate system Z. So to convert from Cartesian coordinate system into the natural coordinate system, then the equation that we derived from earlier slide can be used. which is we know that d z over d, we know that dz over dx is given equal to 2 over le. Then we would like to then solving for dx, then we obtain that dx equal to le over 2 multiplied by dz. So substituting the term dx in the equation by these terms, then we will get the internal strain energy returns as a function of a natural coordinate system, which is given by this equation. Then if we integrate this from -1 to 1, so all over the element until from -1 until z equal to +1, then we will find that if we further simplify this equation, then we will find that the internal strain energy based on the potential energy equation is given by these expressions, which is this term here is something unique, and this is actually called as the elements stiffness metric K. So in this element stiffness metric K is not only contain the geometrical informations of our element, which is the cross sections and the length, but it also contains the material properties of the material used in our problem, which is in this case refers to E, which is the Young modulus of the material. So we have explained this slide just now, so we can move to the next slide. So at least at this stage, we are actually are able to obtain the K for the system of linear equations. Q, which is the unknown, that we are going to obtain Q later, but now is to dealing with the force vector F. So it's mentioned here that the force acting on 1D structures can be of a body force, traction force, and also concentrated force. So this is the three forces that we consider in our application for 1D structures problem, and they may act individually in various combinations. So from the total potential energy, the terms that contains the body force, traction force, and the concentrated forces actually contain in these the last three terms on the right hand side of this potential energy equation. The potential energy due to body force, which is labeled as FP in a single element, is given by the second term, which is this one in the potential energy equation. So from U, which is we know that U equal to N1 Q1 plus N2 Q2, then we substitute this expression into the second term of this potential energy equation, then we expand it. So while we expand it, and also we substitute the term dx by L over 2 dz, then actually we can obtain that the terms that contain the information about the body force is given by this expression here, where the force due to the body force is actually only contained in this part of the equation. which is if we consider the total force that we have here is actually contributing from the body force plus the traction force plus the point load. So for the body force that we can obtain from this equation, which is requires the informations of the geometrical informations of our structures, A, which is the cross sectional area, L, which is the length of the element, FB, which is the amount of force or body force that contained in that particular elements, then we divide it by 2 and then distributed equally to the nodal point. So in this body force, we can imagine that for one element, the body force will always acting at the center of a mass or the center of a gravity. So for whatever mass that contains it at the center of gravity, in this finite element method, we have somehow to translate this force into or equivalence into the equivalence nodal force. So that's mean here the force, the body force, which is initially acting at the center of mass, will be transferred into the nodal nodes equivalently. So that's why in this case, for 1D problem, we have 2 nodes for one element. So the mass that contained in this so the mass that contains at the center of mass should be divided by 2, which is we distribute it equally to the 2 points or to the 2 nodes, which is node 1 and node 2. In these sessions, we are going to discuss about the force due to the traction force. It mentions there that the potential energy due to traction force T is given by the terms or the third equation in our potential energy equation, which is given by ut multiplied by t then multiplied by dx, where u here is actually referred to the field displacement and given by this n1 q1 and n2 q2, and we substitute dx by L over 2 multiplied by dz as in the previous equations. Then if we solve this and integrate the equation by dz, then we simplify and rearrange it, then we will get the terms can be reduced into this the final equation that we have in the slides. The last equation that we have in the previous slide can be written in a compact form, which is in the metric format, which is given by q multiplied by t, where this is actually equivalent to t multiplied by LE over 2, and then substitute, and then we distribute it equally to both nodal point. So in this case, we also can imagine that if we have one element which is has 2 nodal points, and the traction force which is acting on this element, and we distribute it equivalently to each nodal points. So this is what is explained in this equation here. So for traction force, we have TL over 2 multiplied by the column vectors 1 and 1. The point load is actually straightforward, which is the load that applied directly on the nodal points. So whether we have the load that apply to nodes number 1, then it will be labeled as F1, and if we have load that apply to the nodes number 2, then we will have F2. So in this case, we do not need to distribute it equally again, because this point load, or we call it P, because this point load is already acting on this nodal point.